All right, so it is 11:01, so let's go ahead and get started. Again, thank you everyone for attending. My name is Kyle Lake. I am with Oasis Sales, and we are a distributor of Mentor Graphics. We're happy to host today EMI Control Taming the Beast, and we're really trying to hopefully simplify what EMI is all about, find out some of its root causes, and maybe how to mitigate those effects the best way possible. So about our webinar agenda, we're very pleased to have Terry Fox, who's a very renowned industry expert on the causes and minimization of EMI. So that's what he'll be talking about for the first half hour. Then we're going to have Sherwin Davenport, who is a solutions expert with Mentor Graphics on HyperLynx. And HyperLynx is a well-known tool that really helps mitigate and find out why these issues are affecting your boards and your designs. So if you're not familiar with Oasis Sales or Mentor Graphics, we do provide solutions for your entire design of electronics, whether that's the actual schematic design in the schematic and circuit, or simulation and analysis through HyperLynx or any other simulation tools. We really hope to be able to provide you cost savings in general. Just a little bit about Oasis Sales. We have been a premier partner with Mentor Graphics, now a Siemens company, for over 16 years. We like to call ourselves a small band of technical renegades terrorizing the EDA industry, and we, with help of great folks like Terry Fox, we really hope to be able to help you guys out with your problems and help you find solutions. Just a little bit about our tech team. So myself, I am Kyle Lake. I'm an applications engineer. We also have Brent Klingforth. We have two AEs on the board side. I myself am based out of Portland. Brent is out of Colorado area. And if you're interested, if you're actually in our territory and want to hear more about what we can offer you in terms of helping your design process and figuring out some of your different design issues, we have all of our different outside sales teams in their respective locations. Derek Pop, Lizzie Marsh, Andy Bowe. Please feel free to take a screenshot of their information if you need to contact them later and have any other questions. We also have Peter Kilios down there in the Texas region, Rick Truza up in the Midwest, Great Lakes states, and Jason Johnson is as well in the Northwest. We also have an inside sales team with Fawn Chang and Dennis Reynolds. They help mostly with our pads products. And we are available. We're always happy to come help figure out why certain things are happening, to discuss what we can do to provide solutions to your different design issues, whether it's electronics or cable harness, anything like that. We're always happy to help. So there's my contact information as well. Just a little bit about Terry Fox, if he really needs an introduction. Terry Fox has been a long-standing member in the SI community that really has helped write the book on causes, issues, and mitigations. So he can really focus on explaining complex subjects in a very simple yet easily understood fashion that can be grasped by engineers and layout designers together. So he's taught over 500 classes, and we're really excited to have him here today. Okay, so for the agenda today, just what is EMI? Why is it caused? What are things that we can see in designs that might cause EMI in our designs? Key reasons why these are created, and then how to control them. Then we're going to step into why checking for EMI is difficult on a PCB. This is usually something that a very experienced, technically experienced, and very experienced on signal integrity itself has to check manually on a board. Then we're going to talk about what is electrical sign-off and how we can perform that, and how we, as Oasis Sales, can help you in your design process. All right, without further ado, I am going to go ahead and pass this over to Terry, who's going to go ahead and take us through his EMI dissertation. All right, Terry, you ready?
Yeah.
All right. All right, I've gone ahead and made you the presenter.
Okay. So let's see what we got. From the beginning, are you seeing something on your screen?
Yes, we can see your screen.
All right, off we go. Well, my name's Terry Fox, BSCE, Montana State University, 1969. Home for me is in Issaquah, Washington. I started my career selling Hewlett-Packard instruments. If anybody is old enough to remember the Hewlett-Packard encyclopedia of instruments, well, I was one of those guys that ran around explaining that stuff. That was back in the 70s. In the 90s, I started doing signal integrity and EMI work. As of today, I have two sides to the business. One side is training, and I literally have done at least 500 classes all over United States, Canada, I guess as far east as Singapore, China, Beijing, I guess that's west. East would be like England and things like that. South down to Mexico. Anyway, if we look at my past history up through 2013, 75% of my consulting work was what I call disaster recovery. And disaster recovery is basically a project that's probably, I'd say, minimum 6 months late, and they have problems, and all of a sudden it's, gee, how do we get this thing fixed so we can go ship it? Now, of those disaster recovery problems, the vast majority of them were due to EMI test failures. In other words, the product was radiating. So the product works, but it will not pass regulatory tests, and that ends up being kind of a problem. Now, sorry, I had the phone ring in the office and it threw me off my pace here. Anyway, when you have a case that the product works but it will not pass FCC or CISPR tests or DO-160 if you happen to be in the aviation business, the net result of that is you can't ship it. So you might have $5 million into a product development, but you don't get paid because you can't ship the darn thing. Now, with proper signal integrity, power integrity, filtering, and grounding, you will get a 100% pass rate. All right? Now, I'm not hesitating in that. I'm telling you, this is reality, because for the last, I don't know, 20 years, that's something that I've been doing, and I've yet to have one fail as long as we use, you know, the proper, I don't know, understanding of what the problem is. Now, proper simulation-based process shortens the concept to shipping time dramatically, and also dramatically reduces development costs. So this is something that if you can make the paradigm shift and understand what's going on here, then you can shorten the time of your development and also reduce your development costs. So in other words, if you use the SIMC.com procedures, that leads to a product that works at full speed, it is reliable, and it always passes FCC or CISPR EMI tests. Now you notice I didn't stutter. I'm not joking about this. This is something that I have been not only teaching, but I also literally do consulting in this area. And if we had a longer time to do this seminar, which we don't, I could regale you with enough war stories that I could make absolute believers out of anybody. But this stuff really works. First, you've got to understand what's going on. So here we go. If I've got a radiated emission problem, it takes two pieces. It takes energy, and it takes an antenna. Now, if I take energy plus the antenna, I've got radiated emissions. Now, if I have no energy, then there's no radiated emissions. I can have energy but no antenna, and again, no radiated emissions. Now, I can have an absolute disaster inside a Faraday cage, and as long as all of the leads coming in and out of that cage are properly filtered, so the shielding is the Faraday cage, but as long as everything that goes in and out of the cage is properly filtered, I have no EMI. Now, when we go through and do things, we either want to reduce the energy that can end up radiating, or we want to make the antenna less efficient. So I work on both of these, and we do filtering, but the primary lever on this stuff is energy and antenna creation and mitigation. So here we go. If I was to look at a trapezoidal signal on an oscilloscope, let's say this is a 100 megahertz and a 1 nanosecond rise time. So the rep rate on this signal is 100 megahertz. The rise time is 1 nanosecond. And if I was to look at that same signal using a spectrum analyzer, so here I'm in the frequency domain, so if this was 1 gigahertz and 100 megahertz and 1 nanosecond rise time, what I'd see is I'd see 100 megahertz, 200 megahertz, 300 megahertz, 400 megahertz, 500 megahertz, or 600 megahertz. So in other words, this trapezoidal signal looks like this frequency comb, and how far out this thing goes depends upon the rise time of that signal. The spacing of the trees, or the totem pole, the poles, if you will, are going to be based on what's the fundamental repetition rate of this signal. So anyway, we've got trapezoidal signals running around all over the place in digital designs, and the net result is we've got lots and lots of frequencies that are running around in there. So let's understand what makes a good antenna. Now, an antenna has to have two parts that are separated that work off each other. Now, a dipole is a very efficient quarter wave stub on either side of a signal generator. So if I've got a quarter wave this way and a quarter wave that way, and I drive it in the middle, that is a very, very efficient antenna. Now, if the signal current and the return current are closely coupled, this makes a poor antenna. So imagine having an antenna where one lead of the antenna goes this way and one lead of the antenna goes that way. And imagine me taking this and folding it over so both leads are close together. When you've got a signal current and a return current that are close together, i.e. I'm routing on layer 1 and the return current is on the ground plane on layer 2, as long as those things are close together, they basically cancel each other out. They make for a very small loop area in the antenna. Now, if the two legs of a differential pair are the same electrical length, each individually closely coupled to their own respective return current, the pair makes a poor antenna. So imagine something like an Ethernet 10 base T Cat5 kind of cable. Those are just twisted pairs, they're not shielded, but why don't they radiate? The reason they don't radiate is because the plus side of the signal is very, very close to the minus side of the signal, and the current out and the current back basically make fields that cancel each other. So that's what's going on there. Now, when I talked about the dipole antenna, think about what happens if I get noise on the ground plane on a board. So consider the blue here just being ground, GND. And consider these black leads coming out being a ground shield, you know, like one of those big heavy woven ground shields that we see in the military work a lot of times. If you have a big heavy woven military style ground shield with a cannon connector or something like that, so this thing is absolutely connected to that, and that absolutely is ground, and this absolutely is ground. And if I was to take a DC ohm meter, I would find that I've got very little impedance between this point and that point. Now, if you get noise on this ground plane, what you've done is you've created a dipole antenna. This is the noise generator. There's a quarter wave, and there's a quarter wave. And you say, well, Terry, how do you know that that's a quarter wave? Well, if you back up to the previous slide, the trapezoidal wave ends up with this whole comb of frequencies. So we're going to find some frequency that just really likes that distance, whatever that distance is. Now, on the other hand, if I have a signal where here, let's consider this black line as being on layer 1, and then the red line down here is the return current on layer 2, which we would think of as ground, and somebody puts a slot in the ground plane. if the signal current was there and the return current was right here, they would be very closely coupled, just like taking one arm of that dipole and folding it over, and so they're close together. The electromagnetic radiation from one arm would cancel the other one. But when you fold them out so it is a dipole, now all of a sudden they get good coupling, and you know, we're radiating like crazy. Well, now think about this. As soon as you run this signal across a break in that ground plane, we have the return current coming back, but it can't get across this gap right here. That little area is meant to indicate a gap. So the return current has got to go out and around and back. Now, what do you think this has done to the loop area of this antenna? I mean, it's not only the fact that I've got impedance discontinuities, but also I've just created a loop area that is very much larger than not going across that break in the plane. All right. Now, when we talk about radiated EMI, there is differential noise, and that is the direct result of digital switching. And as long as differential noise is properly terminated and you don't do something to interfere with the return current path, i.e. the signal current and the return current are closely coupled, then for the most part, differential noise simply isn't a problem. However, differential mode noise becomes common mode noise when the return current is decoupled from the signal current. Common reasons for this are poor power delivery system design, and that leads to plane noise. And when I've got plane noise, now I've got a signal generator, and someplace in here I've got a ground lead that is probably connected to that ground plane. Or poor routing practice / layer stack up that leads to orphan return current. Now, either one of those things are a problem. Now, the number that I'd like to have you keep in your mind is this. If I have differential noise, so if I had a signal here where I had something running and this was 100 megahertz, not drawing very well today, 100 megahertz, 1 nanosecond, let's call it 10 inches long, 30 milliamps, properly terminated, 10 mils above the ground plane. So if this was 10 inches long, 10 mils above the ground plane, or 5 mils, something like that, 30 milliamps, 100 megahertz, 1 nanosecond rise time, I would not ring the Class B bell for FCC. So in other words, I could have 30 milliamps, 100 megahertz, 1 nanosecond rise time, properly terminated, 5 mils from the ground plane, and I would not exceed FCC Class B for that signal. Now, if I take that same 10-inch long signal and I raise it so it goes up here, and let's put it up there at 10 inches. So it's not closely coupled anymore. It's not within 5 mils. It's up there at 10 inches. In other words, there is a big separation between this signal and that signal. If you do that, I can get this thing to break the FCC Class B bell with 20, see if I can write this correctly, 20 microamps. Now, for those of you that are good with dBs, figure out what 30 milliamps and 20 microamps, what's the difference there? Now, that is over 60 dB. Now, for those of you who have spent any time in a screen room trying to get rid of a radiated emission problem, if somebody came in and said, ooh, just change the rules, you got to drop your levels by 60 dB, most of you would probably, just simply resign on the spot and say life isn't worth it. But the fact is, as soon as you convert anything into common mode, you've caused a tremendous problem, and it's got a tremendous amplifier associated with it. So you never, ever, 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 ever want to create common mode noise. Now, there are common reasons why that happens. But just remember, don't do that. And one of the primary issues in that area are things like noise on your ground planes, which is a good reason for making good power delivery systems. All right, let me back this up. Well, someplace I have lost where I'm at. Previous. Okay, so let's get next. All right, so imagine what happened. By the way, this is a picture that I just ginned up one day when I was trying to explain this problem to some folks that say, well, I've got a ground lead coming off here and a ground lead coming off here, and why is this darn thing radiating? So I said, okay, here is something that came out of HyperLynx Power Integrity Tool. This is a 5x5 array of 0.1 microfarad 0402 capacitors. This was another array of, I'm not sure what size those capacitors were. This is where the voltage was coming onto the system. U21, U22, U23, so on and so forth. Those were various points that were doing something. I guess they were pulling current out of the board. And I had a VIA and so on and so forth. So anyway, the point of it is that in that design, the difference between this point here and this point over here was like over a volt. Now, to put everything in perspective, you only have to have basically microvolts attached to a good antenna, and it will radiate just fine. Nonetheless, I'm going to run out of time before I get through with this. So, moving right along. Pointer options, erase the slide. Okay, now, we have things that I call switchers from hell, and the problem behind it is that any switcher that you put on the board, it's got a controller, it's got some MOSFETs that are on there, some sort of transformer or inductor, then rectifier or filter, and if you looked at these things, these guys are generally switching someplace between a few amps and maybe as much as 10 amps, and they're switching maybe at a megahertz rate or a 2 megahertz rate, but the problem is they probably got sub 2 nanosecond rise times, so consequently these are tremendous noise generators, and you have to know how to implement these without getting into trouble. Now, one of the things you can do is go get Rudy Severin's book, snubberdesign.com, and learn how to speak snubber. I am not a good analog guy, so I know enough to recognize good design, but don't ask me to do it. But what I am is a pretty good digital guy. Now, if I go through and I happen to split the ground plane underneath that switcher, which is a very common thing that people do because they say, well, we're trying to isolate this noise, what they end up doing is causing a tremendous increase in their radiated emissions. And they say, well, why is this? Well, in order to understand why that is, you have to understand how shields work. So here we go. We're back here talking to good old Mr. Maxwell. There are his 4 equations in integral form. We're going to talk very shortly about a version of this that we call Faraday's law. So let's go and look at Faraday's law. Now, Faraday's law says that if I integrate the E field around some path, whatever number I get out of that is going to be directly equivalent to the magnetic flux going through that surface, but it's the time derivative of it. So in other words, don't have time to go through a full explanation. Let's go just take the take this, you know, as a given that that this is true. If I had something where I said, well, I'm going to make the E field equal to 0. How could I make the E field around here equal to 0 if I integrate it around there? Well, it's real easy. Give me a wide zero. Not typing too well. Okay, equal to 0. Let's assume that this thing was wide. It's 10 inches wide and it's made out of gold, so it's a perfect conductor around this way. that would say that the E field is going to always integrate to be 0. Now, if that integrates to be 0, that says that the flux going through here, the magnetic flux, through that area, the time derivative of it, that also has to equal 0. So let's change things a little bit. Let's assume that I was to go through and call this a metal sphere. That way everything is symmetrical. And inside the metal sphere, I've got a guy and he's got his radio in there. So with the radio, he's trying to call out to Rangoon. Up here is, you know, Rangoon, and they've got their big tower and they're trying to radiate down here and get information in. Now, if that bubble, if that ball was made out of plastic, they could transmit through it just fine. If the ball happened to be made out of, say, gold or something, and it's a hollow ball, and that gold is what we call a skin depth thick, then what would happen is that Rangoon couldn't talk to the guy inside the Faraday shield. The guy inside the Faraday shield could not talk to Rangoon, and the reason behind that is because I have forced E equal to 0 at any point it intersects on here, and the net result of that is that that forces this side to equal 0, and when that happens, nobody talks to anybody. Now you might say, why does that happen? The reason it happens is because this incoming magnetic signal causes an electrical current, an eddy current if you will, and that eddy current results in a magnetic field equal and opposite to the field that induced it. So, in short, what do you need for electromagnetic shielding? Well, the biggest thing you need is you need to have a surface that will handle eddy currents. So let's go back to this one more. Let's go back to, come on, where's my, oh, okay, here you go. Now, if you cut the ground plane here, and I've got any sort of noise generator here, then it's pretty easy to imagine that some of those lines are going to go outside of this boundary, and that says that when you cut away this ground plane, you've done exactly the same thing as going out to your kid's trampoline in the backyard and clipping out, you know, 9 out of 10 of the springs, so when they go jump on it, they end up on the ground. Well, I'm running out of time here, so let's try to move on to here. All right, I've also got a video on this stuff, so you can go look at that. So the ramifications of Faraday's law: if you have a closed, perfectly conducting surface, you are forcing E equal to 0 around any loop that can be drawn on that surface. Hence, with a closed zero impedance loop, any change in magnetic field, blah, 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 blah. You can read this stuff. Let's move on to the next one. So when you want to implement a quiet switcher, these are the basic rules. One, I want to have a single point ground. So here, consider everything in the blue as being part of the switcher itself. So I've got a single point ground, so whether it's the DC power in or the DC power out, I've got the single point ground, and this is the point at which switcher ground and system ground or board ground are the same ground. Now, no switcher current on the system ground. So in other words, if you have to have two layers, like layer 1 and layer 2, to handle the routing problem for everything that's inside this switcher, then what you do is you drop down to layer 3, which is normally a routing layer, pour copper down there, stitch it around the outside, so this thing is in essence kind of a bathtub, if you will. Do all your routing inside that area, and then when you come out of that area, you do the single point ground, DC power out, DC power in, away we go. This is just saying if you go and you've got to have capacitors on the back of the board, then we do the same thing on the back of the board. All right. Now, when we talk about grounding, this is another place where it causes great difficulty. I can either have a single point ground or an everywhere ground. If I've got a single point ground, that says that any current flowing into this area flows out along the same path. So in other words, that's a small antenna. Now, as soon as you give me a second point anywhere, now I've got this situation. It can flow in from this side, and it can return through that side. The previous one, this is a small antenna. That is a big antenna. Don't do that. One of the things that we try to do is always get these connectors on the same side of the board so we get rid of those problems, because you'll always have some noise on the board. If you do a good job of power integrity, work and making quiet power delivery systems, then you get a lot less noise, but you'll always have some. All right, so product becomes an unwanted radio transmitter and cannot ship because it fails regulatory tests. Key reasons. Number one, multiple grounds connected to off-board leads. Signal ground, chassis ground, analog ground, RF ground, etc. Anytime that I get outside of the box and you've got something with a noun in front, or a modifier in front of the word ground, I know we're going to have trouble. The second thing is the power delivery plane noise coupled with bad connector placement. Poor connector or cable strategy. You've got to know what you do when you get off there. Poor signal integrity. In case anybody hasn't figured this out yet, ringing is the root of all evil in this business. And if you don't take care of ringing first, you're just creating a whole lot of noise, and it's very difficult to go control that once you generate it. So ringing, crosstalk, ground bounce, all of these things create more noise. Now, poor routing practice creates antennas. In other words, you're taking something that was differential in nature and making it common mode in nature, and that's where you get into that 60 dB plus kicker that really causes problem. Crosstalk onto I/O leads, poorly implemented DC to DC converters, chips from hell. There are chips that were not packaged correctly, and so those do exist. Now, if you're using chips that are common in the industry, no problem. Last thing, inadequate filtering and shielding. So to control this, what do you have to do? First of all, control ringing. This is the basic engine of all noise. Second of all, never lose or abuse the return current path. This is a common mode noise generation mechanism that gives you a 60 dB increase in radiation for the same signal current. Control crosstalk. Keep noise off status type signals that may be a good antenna. Filter every lead that leaves the system. Now, filtering is just fine if we're talking about a signal. How do you filter ground? There is no filter for ground. Ground is ground. That's the reference. So that's the reason I want to keep those connectors close together as far as the ground leads. And I want to keep noise off the ground plane in the first place. Design your power delivery system appropriately to facilitate quiet planes. Now, if you use HyperLynx PI, you can see what the noise is. And then if you just use some good standard practices, you can get that noise down and life's a lot better. Have an unbroken ground plane, making all ground leads common across the entire full frequency spectrum. By the way, you're going to get into arguments with both RF people. You're also going to get into arguments with analog people that are forever trying to cut up these ground planes. Don't have time enough to get into that rant. I'm already 5 minutes over. Place connectors close together, blah, blah, blah. Don't create a dipole antenna with a noise generator in the middle. This is me. Since there are obviously no time to take questions from me, just email me with your questions. There's my email address, and Kyle, you've got it.
Terry, thank you very much. Sorry to make you rush, but yeah, I think you covered some great basics. And again, everyone, if you need to inquire a little bit more about Terry or more of his services or any of his knowledge, feel free to take a screenshot of that or copy it down, and he'll be able to get back to you.
Yeah,
all right.
There are a lot of free videos on my site you can go look at.
Okay, great. Yeah, everyone, you can definitely check Terry out. on his website, siemc.com, and there's some good videos and good content up there. All right, well, thanks again, Terry. And up next, we do have Sherwin Davenport, who is going to talk a little bit further on what we can do about how to mitigate these effects and identify them in your design.
Hello, this is Sherwin Davenport. Welcome to this presentation on accelerating electrical sign-off with HyperLynx. Today we will be discussing how the HyperLynx family of products can be used to validate your PCB designs to a level of confidence that can be considered a sign-off. Our agenda today will include a description of the sign-off problem and an overview of the HyperLynx tools that address sign-off requirements. Nearly all designs have problems when they're first created. Finding these problems can be a big challenge. Even if you simulate, do you simulate all nets? How do you analyze for EMI effects? Do you know that your power distribution network will work at DC and over a wide range of frequencies? So many companies approach these problems with a difficult process involving design guidelines and many independent reviewers. Visual inspection is also used to try and find issues in a layout that may cause problems. This is so time-consuming and error-prone that often every check is not done with the same level of quality. Also, experts are used to validate electrical issues on the board, and this creates a further bottleneck, slowing the process down even more. Okay, so what is sign-off in terms of PCB design? It's a process of verification that a design must complete before it can be sent to manufacturing. So this terminology has been used with IC design for many years, where a process is needed to ensure that all checks have been completed and the designs will not have to be respun. As the complexity and sophistication of PCBs gets greater and the tolerance for schedule delays gets less, a formal sign-off process is becoming more critical to a project's success. Current efforts at achieving sign-off are full of manual checking and rechecking, and they rely too heavily on a few experts to review too many designs. The ability to validate designs has to become more automated, and it has to be made accessible to the board designers. This is the only way to reduce the bottleneck. So on the current board designs, high frequency and high edge rate signals are creating electrical issues all over the board. With that, an improved sign-off process is really needed to remove the bottlenecks and to ensure all the critical issues are checked with complete and repeatable methods. New signaling technology is leading to more coupling and EMI problems than ever before. All right, let's look over an example of some requirements that you might have on your next design. Suppose that you know that you need to meet signal quality requirements for overshoot, ringback, monotonicity, and that timing on your DDR and other interface needs to be checked. You also have to look at the power distribution network for current density and decoupling, and you have thermal issues you need to consider. There's also high-speed serial links on the board that have to perform at certain levels, and many EMI and crosstalk problems that need to be checked. How will you address all these requirements so that you can sign off on the board with confidence? Ideally, we want to capture the expertise of SI and EMC experts in such a way that rules could be written to run on entire designs, checking all the nets in a way the expert would if he had time. That way, PCB and hardware designers could participate more effectively in the checking and signing off process. So Mentor has the tools to help you achieve a total sign-off solution. Tools and checks exist to validate boards for layout, EMC, signal integrity, power integrity, manufacturability, and even thermal compliance. All of these necessary checks are integrated into the Mentor environment. All right, here is the electrical sign-off process we're suggesting. Use pre-layout analysis to determine layout constraints. After or during layout, you run the HyperLynx DRC rule set to ensure no violations were introduced. Then use signal and power integrity simulations to investigate areas that might be issues. Also use signal and power integrity simulations to verify design compliance for requirements that cannot be checked with rules. The cornerstone of this automated validation and sign-off process is HyperLynx DRC. This tool was created specifically to capture critical electrical checks and rules and apply them to boards with thousands of nets. Its built-in rules are included that check for many common issues, and custom rules can be created to check for issues specific to your company or technology. HyperLynx DRC accelerates the sign-off process. It reduces the time it takes to complete the final design. It's easy to use, so many people can get involved, but everyone will be running the same rigorous checks. It can find problems that simulations can't, and alleviates the bottleneck caused by having to run many checks through an expert. Finding these errors before the board is built saves time, money, and field failures. HyperLynx DRC can find problems that require detailed simulations, and that could be located anywhere on the board. Since it has an integrated field solver, it can easily find issues related to impedance and crosstalk. HyperLynx DRC includes 23 built-in rules. They're organized into EMI, SI, and PI groups. Extensive and detailed documentation is included on each rule, right in the tool, so it's clear how to set up the parameters and what the rule is checking for. For example, the reference plane change rule looks for a situation where a signal changes the plane that it is referencing. This could happen through a via transition or by the trace being routed to a new plane area and leads to a potential long return path. Another check looks for traces that are near the edge of a board, which might radiate EMI. The crosstalk rule in HyperLynx DRC checks every net and looks to see if there might be coupled crosstalk in excess of a threshold voltage. A summary report can be generated showing the worst offenders that might then need additional signal integrity analysis. We'll take a look now quickly at HyperLynx DRC. We brought in a board. We can bring in boards from all sorts of places. We obviously can do it from all the Mentor tools. We can use O2B++, which is pretty generic. Anyone can generate that. It's actually a pretty good source. But then there's some others that come directly from various other vendors. So there shouldn't be a problem getting the board in here. When the board does first come up, it's going to launch a wizard which will step you through clarifying that the steps it's going to take to figure out what's going on in the design are the ones that you want. So we're really looking for, what are the termination components? What are the connector components? So, and also, of course, what are the high-speed nets and the constant nets? We want to get a full understanding of all of that. And you can see we've kind of already broken that up. We've got electrical net understanding, so we know there's termination going for a signal net. The entirety is an electrical net there, so we've got that understanding going on as well. Anyway, so once we've got the basic premise set up, we can go off and start running the rules. And we've got our EMI rules, we've got SI and PI rules. So right here I've got a few EMI rules that I've already run through. On these, you can go ahead and select one of these and come down here to the spreadsheet There's a picture here which kind of describes what it's looking at. So this is looking for cases where high-speed nets run close to other nets which happen to go to connectors, which is why we need to know what all the connectors on the board are. And the crosstalk between those two could cause enough noise that then could become an antenna or a radiated on this net that kind of acts as an antenna off the board. Other things like metal islands, so just pieces of copper that aren't attached to anything. These are creating little antennas that are hanging around on the board. Another one, nets crossing gaps. So you got a net coming along. You've got that gap there. Essentially, that's an antenna. And there's a few other ways that we can create those. We don't want those, so we need some way to deal with that. Putting a capacitor close by can help out with that. Anyway, with any of these, we just select a rule. We'll stay with net crossing gaps. We can look at the violations, and this will show you a list of those nets that have those issues. So we've got a net crossing a split here. We can zoom out a little bit to see what's going on. That one's pretty small. Next, you see it's ranked as rank 4. Let's sort this around. So rank 1, those are going to be the bigger ones that are spending more time out of a reference plane area. So that net is pretty much all out of, not covered, but it might not be a high-speed net, or it might be. Anyway, so those are things we might want to narrow down, but these are traces that are spending a lot of time uncovered, different impedances. So those are just leaving traces. We've got crossing gaps where it's going from one reference plane to another. And so we can work through and see where those errors are, and then go find a way to work with that in the simulation tools. We can also create a share list. So if we want to give this information to someone else who doesn't have access to the tool, we build up a share list, and this will save out a little snapshot of what's going on and the information that we have here on the line of that error, so that person can still see the issue and understand what might need to be done to be fixed on that. So that's kind of the HyperLynx DRC tool in a nutshell. There's a lot more to it, lots of different rules, but I think that gives you a general idea. After you've used HyperLynx DRC to find the areas of the board that need further attention, you could go back to HyperLynx SI to do some of that work. First, let's look at a generic way to analyze a large number of nets on a board. HyperLynx Generic Batch Simulation can analyze all the nets on your board and provide a spreadsheet summary of violations. The required values and margins can be entered as rules, so that you can not only determine that a net passes a test, but also by how much. Timing analysis is always a part of board verification. The generic batch simulation produces an IEEE standard SDF output that includes compensated flight times for each net. These values can be used in a timing analysis tool or spreadsheet. Mentor also offers DDR Wizard, which provides comprehensive timing checks for all nets in the standard DDR interface. This type of complete and detailed timing analysis is virtually impossible to do by hand. Power planes have to be able to supply enough current to maintain the supply voltage at every power pin on every IC within tolerance. HyperLynx DC Drop calculates the plane voltage and current density at every point, and also reports via and pin voltages and via currents in a summary spreadsheet. This report could be a standard part of the sign-off document in your PCB design process. ICs on boards also need to draw transient current to supply the fast edge rate drivers in modern designs. The impedance between a power and reference plane shows how well the power distribution network can supply current quickly, and also how much noise voltage this produces on the planes. These are common requirements specified to ensure a high performance design. After you've run HyperLynx DRC and you've found where some of the issues are that you want to investigate a little bit further, you can bring up the board here in HyperLynx SIPI tool, And with this, you can go ahead and focus in on certain nets. There is a batch mode simulation you can run to get additional information on where it thinks you should look. That is where the tool thinks some of the issues might be based on simulation results. Or you can go in and look at specific nets like I've clicked on here. And I guess the nice thing here with this is we've got complete models of every segment and the vias and the way that they attach to the parts. And that gets included in the simulation. We just need to attach some IBIS models to the ends of those. And then we can go ahead and run some simulation to see how the signal integrity would look. Let's take a look at one particular simulation. Let's go in and look at the power integrity DC drop simulation. So this is a simulation where we pretend that we've got that all your ICs are just pulling at a constant rate. They're not really going to be doing that, but we just kind of guess at the worst case how much current they're going to draw, and then we determine if the power supply is able to, the power supply and the power rails are able to supply current and voltage appropriately to the entire device. So we assign models to the input. Where's the power coming from for this power rail? Where's it going to in this power rail? So on this 1.5 volt power rail, we've got power coming in up here, and then a couple chips and another device there pulling power from there. So we can just go ahead and run the simulation, and we're going to get two outputs from that. One is a report that tells us what the current and voltage is at each of the power pins, and then we also get the current and voltage at each of the vias, as we can see over here, so you can kind of pinpoint hot areas that way. The other way is through a scope that we get back here, which is showing us the right now we're looking at current density. So this is how much current is flowing at particular parts in the design. This one might be a little bit easier to look at if we flatten it down like that, and then you can kind of change the scale back and forth to get a feel for where those hot spots are. But let's go ahead and zoom in here on this area here. We've got over 100 milliamps per mil squared. That's probably not good. This is maybe 50 amps or so for mil squared, not too bad. And then where the power is coming in, we're getting a hot spot there. This one's getting up above 150 somewhere. So anyway, so that's the current. Definitely some concerns there. Let's change this back to, or over to the DC drop. A little bit different picture here. This is going to give me a 3D view both in height and in color, showing me the voltage as it drops from this point up at 1.492, so almost 1.5 volts, down to 1.436. So again, we're just trying to determine if everything was pulling at its max rate, am I going to get the appropriate voltage to every component on the design? And this may not be adequate, so I probably need to add some more copper in there to that area. So those are the kinds of simulations we can run in HyperLynx SIPI tool to help give you more insight on how to fix the problems that HyperLynx DRC has identified. Thermal compliance is also a common requirement that is becoming more important as electronic devices become smaller and denser. HyperLynx Thermal can quickly provide a thermal profile of the board, helping the designer optimize placement. Many issues can be found this way before the final thermal analysis is conducted. By co-simulating with DC drop, the current density in the planes can be converted to thermal heating in HyperLynx Thermal, giving a complete picture of all heat contributions. Mentor also offers advanced thermal analysis in the FlowTherm product. Serial link interfaces, such as PCI Express, are common on many board designs today. They typically have to conform to a certain bit error rate. Advanced analysis techniques such as 3D electromagnetic modeling need to be used for signals at these frequencies. IBIS AMI models and S-parameter models are used to model key elements of the channel. With this HyperLynx technology, a high-speed serial link can be validated to conform to sign-off requirements. Any sign-off process will require summary reports. Many of the tools we've discussed today can write detailed output in Excel or HTML formats, making it easier to incorporate these reports into your sign-off documentation. By running through these HyperLynx SI, PI, and DRC checks, you can validate your sign-off checklist and verify that you've tested all these requirements and that your design is in compliance. You then know if you have achieved sign-off. In summary, complex printed circuit boards need to be designed right the first time. They need to be checked to validate that they comply with the design requirements, but this can be a big job. HyperLynx products can help streamline the process and make it possible to achieve sign-off in a reasonable amount of time. The sign-off process can reduce the risk in PCB design and lead to higher quality designs that work right the first time. Thanks for spending some time with me. I hope this slideshow has been helpful for you.
Hello, this is Kyle again. I found out that we had some serious sound echo, and I really do apologize for that. I don't see any other questions currently about that, about our other top topics that we covered today. If there are any other questions about what we actually covered today, you can either ask those in the chat box right now. We would happily get to those, or we can definitely have you contact us later, and we can also get back to you then as well. And I'll put my stuff up, my contact information back up on the screen here. So this is just a recap of what we saw today. So we were discussing HyperLynx DRC, and if you were interested in learning a little bit more about that, we are definitely pleased to talk about with you a little bit more, see how that can fit into your organization, maybe tackle some of your design issues, and maybe even look together at a design and see where we might be able to help. Please get back to us, and we would be happy to set that up. We are able to offer up to a 45-day evaluation license if that feels like it would be something that you would like to take a look at, play around with in your own designs, and see how that may help. Okay, so once again, here's my contact information. Again, my name is Kyle Lake, and you can reach me at that email address at kyle.lake@oasissales.com. Okay, and there's my phone number as well. All right, so I'm still not seeing any other questions. So with that, just an FYI, we did record this session. So if you would like to record it again, and hopefully I'll be able to clean up that double audio, we will have that up on our YouTube channel, and we will send out a link to that as well. Okay, well, thanks again for attending, and I hope you all have a good rest of your day.